What if I told you the universe is tearing itself apart, not in some dramatic, explosive way, but silently, invisibly, stretching space itself wider every second? And here's the strangest part, no one knows why. For decades, scientists have been staring into the cosmic abyss, utterly baffled by a force so powerful it overcomes gravity itself, pushing galaxies away from each other faster and faster. They call it dark energy, a ghostly presence that makes up nearly 70% of the universe, yet remains one of the greatest unsolved puzzles in all of science. Picture this, you're holding a balloon and instead of deflating, it starts expanding uncontrollably, no matter how tightly you grip it. That's exactly what's happening to our cosmos right now. Galaxies aren't just drifting apart, they're being flung away by something we can't see, can't touch, and barely understand. It's as if the universe has a hidden engine, and we're only just beginning to hear its faint whisper. This isn't science fiction, it's the reality astronomers face every time they peer through their telescopes, confronted by a mystery that defies every expectation. But what if I told you dark energy is just the beginning? Over the next 25 cosmic revelations, we're diving into the deepest enigmas of the universe, questions that challenge everything we think we know. From phantom energies that rewrite the laws of physics to cosmic voids so vast they shouldn't exist, each mystery pulls us further into the unknown. And here's the thrilling part, you're coming along for the journey. Together, we'll unravel the secrets of this invisible force, explore mind-bending theories, and maybe, just maybe, catch a glimpse of the universe's best-kept secrets. So buckle up, the cosmos has been hiding its greatest tricks, and it's time to uncover them. Scientists once believed the cosmos would slow down over time, like a ball tossed upward, gradually losing speed to gravity's pull. But in the late 1990s, two teams studying distant supernova made a spine-tingling discovery. The universe wasn't just expanding, it was accelerating, as if some unseen hand had pressed down on cosmic gas pedal. Those exploded stars, billions of light-years away, appeared dimmer than they should have been, betraying a truth more startling than anyone imagined. Space itself was stretching faster and faster, pushing galaxies apart at speeds that defied all predictions. This wasn't just a minor tweak to the textbooks. It upended cosmology. Einstein's equations had allowed for such a possibility, a term he'd once called his greatest blunder, but until then, no one took it seriously. Suddenly, scientists had to reckon with the idea that 70% of the universe's energy budget was something utterly unknown: dark energy. Think of it like this: if the cosmos were a pie, the stars, planets, and galaxies we see would be a sliver. Dark matter, another mystery, makes up a larger slice, but dark energy, it's the whole rest of the pie, an invisible force woven into the fabric of space itself. The evidence keeps mounting. The Hubble Constant, which measures how fast the universe expands, shows discrepancies depending on where or when we look. Observations of ancient light from the cosmic microwave background clash with modern measurements of nearby galaxies, creating what scientists call the Hubble tension. It's as if the universe left us two different instruction manuals, each telling a slightly different story. And then there's the eerie uniformity of it all. Dark energy appears perfectly balanced, neither too strong nor too weak, as if fine-tuned by some cosmic architect. Yet for all we've uncovered, the deeper questions remain. Is dark energy truly constant, or could it change over time? Some theories suggest it might grow stronger, eventually ripping apart galaxies, stars, even atoms in a far future cataclysm called the Big Rip. Others propose it's tied to strange new fields or dimensions we've yet to perceive. Every answer leads to 10 new mysteries, and that's what makes this puzzle so electrifying. We're not just observers of the cosmos, we're detectives, piecing together clues from the faint glow of dying stars to the silent echoes of the Big Bang itself. The hunt to unmask dark energy has led physicists down some wildly different paths, each more bizarre than the last. Take Einstein's cosmological constant, that infamous blunder he scribbled into his equations to keep the universe static. Turns out it might have been prophetic. If dark energy is indeed a constant force baked into empty space itself, it would mean every cubic centimeter of the cosmos, even the vacuum inside your coffee cup, contains a faint hum of repulsive energy. But here's the twist: when astronomers calculated how strong this energy should be based on quantum theory, the numbers came out a staggering 120 orders of magnitude too large. That's like expecting a whisper and getting a sonic boom powerful enough to vaporize galaxies. Clearly, we're missing something fundamental. Then there's quintessence, the rebel theory that turns dark energy into a cosmic chameleon. Unlike a static cosmological constant, quintessence imagines a dynamic field that ebbs and flows across space and time, a fifth fundamental force, hence the name, that could weaken or strengthen as the universe ages. Picture it like cosmic weather, sometimes a gentle breeze nudging galaxies apart, other times a gale force wind tearing at spacetime itself. This could explain why dark energy's effects seem finely tuned today. Maybe we're just living during a quiet spell in an ever-changing cosmic storm. But proving it, that's where things get thorny. Quintessence leaves no fingerprints except its subtle grip on expansion, forcing scientists to become cosmic archaeologists, digging through 13.8 billion years of universal history for clues. Enter DAISY, the dark energy spectroscopic instrument, a night sky scanning behemoth with 5,000 robotic eyes, each capturing light from distant quasars and galaxies. By mapping how these celestial objects move apart over time, DAISY aims to catch dark energy in the act, revealing whether it's truly constant or shifting like sand. Early data already hints at surprises. The universe's expansion might not follow the smooth curve we expected. It's as if we've been reading a mystery novel only to find key pages smudged, the plot twisting in ways no one predicted. Yet for all our tools and theories, dark energy remains a riddle wrapped in an enigma. Is it one unified force, or could multiple phenomena be masquerading as a single entity? Some physicists even speculate it's not energy at all, but a sign that Einstein's gravity equations need rewriting at cosmic scales, like using a Newtonian pocket watch to time a black hole collision. With every observation, the mystery deepens, reminding us that the universe still holds cards close to its chest. And that's the exhilarating part. We're not just solving a puzzle. We're rewriting the rules of reality itself. Among the most tantalizing breadcrumbs in our hunt for dark energy lies an ancient snapshot of the universe, the cosmic microwave background. This faint glow, the cooled remnants of the Big Bang's fiery dawn, should be uniformly splashed across the cosmos like spilled ink on paper. But when scientists scrutinized the most precise maps ever made, like those from the Planck satellite, they found something unsettling. The cosmos isn't playing fair. Take the so-called axis of evil, not some comic book villain, but a bizarre alignment in the CMB's temperature fluctuations that point suspiciously toward certain constellations. According to standard cosmology, these primordial ripples should be randomly scattered, a cosmic fingerprint with no preferred direction. Instead, they seem to whisper about an invisible axis, a cosmic tilt that makes no sense under current physics. It's as if the universe hung a keep out sign along this mysterious corridor, and we're only now noticing. Some researchers wonder, could this anomaly be dark energy's calling card? A shadow of its influence etched into the infant universe. Then there's the cold spot, a sprawling region in the constellation Eridanus where temperatures dip dramatically, like a bruise on the sky. Simulations suggest such extreme features should appear maybe once in every 10,000 universes, yet here it is staring back at us, one radical explanation. A collision with another universe during inflation, a cosmic fender bender leaving behind a dent. Others propose it's evidence of dark energy's uneven pull, warping spacetime in ways we're only beginning to grasp. What makes these glitches so electrifying is how they defy the cosmological principle, the bedrock idea that the universe should look roughly the same in all directions. Planck's data reveals other quirks, like hemispheres with oddly mismatched temperatures and large-scale patterns that statistically shouldn't exist. Each anomaly is a crack in the foundation of our understanding, hinting that dark energy might not just be accelerating expansion, it could be twisting the cosmos into shapes we've yet to decode. The stakes couldn't be higher. If these patterns aren't statistical flukes but real features, they might demand entirely new physics, extra dimensions, modified gravity, or even a universe far stranger than we've dared to imagine. Future telescopes, like the James Webb Space Telescope's successors, could scan the CMB with even finer precision, hunting for echoes of dark energy's first whispers. For now, these cosmic irregularities remain one of science's most tantalizing known unknowns, a puzzle written in the oldest light there is, waiting for us to decipher it. If measuring the universe's expansion were as simple as reading a speedometer, we'd have cracked dark energy's secrets long ago. But here's the cosmic curveball. Depending on how we measure it, the universe seems to be expanding at two different speeds. Astronomers call this enigma the Hubble tension, a glaring mismatch between the expansion rate calculated from nearby galaxies and the one inferred from the afterglow of the Big Bang. It's like checking your car's speed with two different GPS devices and getting wildly different numbers, except in this case, the discrepancy could rewrite cosmic history. Start with the local measurements. By tracking the flicker of Cepheid variable stars, celestial lighthouses whose pulse rates reveal their true brightness, scientists can gauge distances to nearby galaxies. Combine this with the redshift of those galaxies, how much their light stretches as space expands, and you get today's expansion rate, roughly 73 kilometers per second per megaparsec. That means for every 3.26 million light-years you look outward, space is stretching 73 kilometers per second faster. Simple, right? Except when we turn to the cosmic microwave background, the universe's baby picture, the math tells a different story. The Planck satellite's ultra-precise maps of this primordial light suggest an expansion rate of 67 kilometers per second per megaparsec, a full 9% slower. 9% might not sound like much, but in cosmology, it's a canyon-sized gap. These two methods are rock solid in their own domains, yet they stubbornly refuse to agree. It's as if the universe played a trick on us, changing the rules between its youth and adulthood. So where does dark energy fit in? If it's truly a constant force, as Einstein's cosmological constant suggests, these measurements should align. The fact they don't hints that dark energy might be more complicated, perhaps growing stronger over time, or interacting with dark matter in ways we haven't imagined. Some theorists even propose an early burst of dark radiation, that briefly turbocharged expansion, throwing off our cosmic calculations. Others wonder if we're seeing cracks in our model of gravity itself, like shadows of extra dimensions warping spacetime on colossal scales. The Hubble tension isn't just academic quibbling, it's a potential seismic shift in our understanding of reality. If local measurements are correct, the universe might be younger than we thought, by hundreds of millions of years. If Planck's data holds, dark energy could be weirder than we dreamed, evolving in ways that defy textbooks. Right now, telescopes like JWST and Vera Rubin Observatory are racing to settle the debate, hunting for new celestial yardsticks like red giant stars or merging neutron stars. Every new data point tightens the noose around this mystery, forcing us to ask, is the tension a flaw in our tools or a clue to dark energy's true nature? One thing's certain, the cosmos loves a good plot twist. Could the greatest cosmic mystery of our time be nothing more than a mirage? Some physicists are daring to ask an explosive question: what if dark energy doesn't exist at all, and we've just misunderstood gravity? Imagine rewriting the most fundamental force in the universe, tweaking its equations to explain the accelerating expansion without invoking an invisible, enigmatic energy. It's a radical idea, but not without precedent. Enter modified Newtonian dynamics, or MND, a theory that boldly suggests gravity doesn't weaken as sharply over vast distances as Newton and Einstein predicted. Instead, it tugs a little harder on galactic scales, potentially explaining why outer stars in galaxies rotate faster than expected without needing dark matter's invisible grip. But here's the twist. Could a similar tweak also account for dark energy's effects? Proponents point to eerie symmetries. Just as MND replaces dark matter with adjusted gravity, theories like FR gravity propose that Einstein's equations need a cosmic scale update, introducing extra terms that mimic dark energy's repulsive push. Picture gravity as a rubber band. Standard physics says it stretches predictably, but modified gravity suggests it might suddenly stiffen over cosmic distances, creating the illusion of an invisible force. Yet the devil's in the details. While these alternatives elegantly sidestep the need for dark energy, they struggle to explain all the evidence. Take the cosmic microwave background's crisp snapshot of the early universe. Its intricate patterns align almost perfectly with dark energy models, while modified gravity theories often require clumsy adjustments to match the data. Then there's the bullet cluster, a cosmic collision where gravity's pull clearly separates from visible matter, leaving modified gravity scrambling to explain the mismatch without invoking dark matter's hidden mass. Most scientists still bet on dark energy, but not out of stubbornness. The cosmological constant, despite its quantum headaches, remains the simplest fix, a single number slotting neatly into Einstein's equations. Modified gravity, by contrast, often feels like retrofitting an old car with experimental parts. It might run, but the repairs grow increasingly convoluted. That said, the debate is far from settled. Future experiments like the European Space Agency's Euclid telescope could tilt the scales, hunting for subtle distortions in galaxy shapes that might betray gravity's true behavior. Whether the answer lies in an unseen energy or a rewritten law of physics, one thing's certain: the universe is forcing us to question our deepest assumptions. And that's where the real discovery happens, not in confirming what we already know, but in uncovering just how much we've yet to understand. Of all the fates the universe might face, none chills the blood quite like the Big Rip, a scenario where dark energy doesn't just push galaxies apart, but grows exponentially stronger, clawing at the fabric of spacetime until reality itself unravels. This isn't some distant sci-fi nightmare. The math suggests it could happen in as little as 22 billion years, a blink on cosmic timescales. The key lies in a terrifying flavor of dark energy called phantom energy, whose repulsive force doesn't just persist, it escalates. Picture a car accelerating not just steadily, but with the pedal slammed to the floor, its speed climbing toward infinity. Here's how the doom spiral would unfold. Today, dark energy's grip is subtle. It overcomes gravity's pull on galactic scales, but matter still holds itself together. But if phantom energy's equation holds true, its strength would amplify until no force in the universe could resist it. First, galaxy clusters would be wrenched apart, their gravitational bonds snapping like frayed ropes. Then, individual galaxies would fly apart, stars scattering like shrapnel. Next, solar systems would disintegrate, planets torn from their orbits, flung into the void. The final act, even atoms would be ripped apart, nuclei splitting as the space between particles stretches faster than light can bridge. The critical factor is something cosmologists call the equation of state, represented by the letter W. For ordinary dark energy, W equals -1, a constant push. But phantom energy demands W be more -1.1 or worse. Each decimal point nudges the universe closer to oblivion, shortening the countdown to the rip. Some models even suggest phantom energy could create space-time bubbles where the laws of physics break entirely, birthing new universes in the carcass of our own, cold comfort for anything caught in the shredding. What's unnerving is how little it would take to tip the scales. If future measurements find dark energy's strength increasing by even a fraction of a percent, the phantom scenario vaults from theory to inevitability. Telescopes are already hunting for clues like whether supernovae in different cosmic eras show telltale changes in brightness, hinting at dark energy's evolving ferocity. For now, the Big Rip remains one possibility among many, but its mere existence forces us to confront a humbling truth. The universe's darkest energy might not just hide in the shadows, it could be biding its time. Here's something that keeps cosmologists up at night. Dark energy didn't just show up, it waited. For billions of years, gravity ruled the cosmos, pulling matter together into galaxies and clusters. Then, around 5 billion years ago, as life was stirring on Earth, something flipped. Dark energy quietly took over, as if the universe had been holding its breath before hitting the accelerator. This eerie timing isn't just curious, it's suspicious. Why would the cosmos spend most of its history under gravity's reign only to switch allegiance so late in the game? Scientists call this the coincidence problem, and it's one of the most haunting loose ends in modern physics. Think of it like walking into a movie halfway through and catching the climax at the exact moment you sit down. The odds feel impossibly slim. If dark energy had asserted itself earlier, galaxies might never have formed later, and we'd never notice its effects. Yet here we are, alive at the precise cosmic instant when dark energy's push and gravity's pull are almost balanced close enough to measure both. It's as if the universe conspired to make its greatest mystery observable just as intelligent life arose to ponder it. This cosmic déjà vu has led some theorists down a controversial path, the anthropic principle. The idea suggests that dark energy's timing isn't random at all, it's a prerequisite for our existence. In a multiverse teeming with countless universes, each with different physical constants, only those with dark energy values permitting galaxies, stars, and planets would ever host observers to notice. We're not seeing a bizarre coincidence, we're seeing the one version of reality where the numbers lined up just right for life. It's less a grand design than a cosmic selection bias, like a lottery winner marveling at their odds without considering the millions who didn't get a ticket. But not everyone finds this satisfying. Critics argue it's a philosophical shrug disguised as science, an excuse to stop searching for deeper laws. Enter string theory's landscape, a dizzying array of possible universes predicted by the math, each with different constants. If reality is a vast patchwork of these universes, ours might simply be one where dark energy's value lands in the habitable sweet spot, the catch proving it. Multiverses are, by definition, beyond observation, leaving the anthropic argument lingering in a scientific gray zone, too compelling to ignore, too untestable to confirm. Meanwhile, others hunt for dynamical explanations. Could dark energy interact with dark matter, its influence waxing as the cosmos evolves? Or is our three-dimensional universe brushing against hidden dimensions, leaking gravity and amplifying dark energy's effects over time? Each theory dances on the edge of plausibility, offering glimpses of a solution without definitive proof. The real shock isn't just that dark energy dominates now, it's that we're here to witness it at all. Whether through multiverses, unseen dimensions, or laws we've yet to dream up, the coincidence problem forces us to confront an uncomfortable truth. The universe might not need to make sense to us. And that's precisely what makes the hunt so thrilling. Every unexplained detail isn't a dead end, it's a signpost pointing toward something deeper, something stranger. The cosmos has never played by our rules. Why start now? The cosmic future is a silent countdown, ticking toward scenarios so vast they dwarf human imagination. If dark energy continues its relentless push, the universe won't just expand, it will dissolve into darkness, one galaxy at a time. Picture the night sky millennia from now. The constellations we know will have fractured, their stars pulled beyond an invisible barrier called the cosmic horizon. Light from those distant galaxies, no matter how bright, will stretch into oblivion, their wavelengths dragged so long they fade from detectability. Our Milky Way will stand alone in an ever-blackening void, the last island in an ocean of nothingness. This is the heat-death scenario, where dark energy's victory leaves the universe cold, empty, and eerily uniform. Simulations paint a chilling portrait. First, galaxy clusters like Virgo and Coma vanish from view. Then, local group galaxies Andromeda, the Magellanic Clouds rip away, their light stretched to infrared whispers before disappearing entirely. Eventually, even stars within our own galaxy will drift apart, their fuel exhausted, leaving behind black holes that evaporate over inconceivable trillions of years. The end result, a cosmos so diluted that not a single particle interacts with another, a frozen wasteland where entropy wins and time loses all meaning. But heat death isn't the only possibility. Some theories suggest dark energy could weaken or reverse, allowing gravity to claw back dominance in a big crunch. Imagine the expansion slowing, halting, then collapsing inward like a deflating balloon. Galaxies would rush toward each other, merging in violent embraces until all matter is compressed into a singularity, a rebirth point for another Big Bang. This cyclical model offers a poetic symmetry, a universe perpetually dying and reviving. Yet current data leans against it. Dark energy's grip seems unrelenting, making collapse unlikely unless our understanding of its nature is profoundly wrong. Then there's the wild card, vacuum decay. If our universe isn't in the lowest energy state, if there's a truer vacuum lurking beneath reality, a quantum fluctuation could trigger a bubble of true vacuum expanding at light speed. Inside that bubble, the laws of physics rewrite themselves, obliterating everything in their path. Dark energy might play a role here, its instability nudging space-time toward this apocalyptic phase transition. One moment the cosmos exists, the next it's erased, replaced by something utterly alien. The most haunting question isn't just how the universe ends, but when. If dark energy behaves as a true cosmological constant, heat death might take 10 to the 100th power years, a number so large it's meaningless to human minds. But if phantom energy is real, the big rip could arrive in a mere 22 billion years, shredding reality before the sun even cools. Telescopes like JWST and future missions like LISA might spot clues, subtle changes in dark energy's strength over cosmic time, or anomalies in how the most distant galaxies recede. What's certain is this: dark energy isn't just a curiosity. It's the architect of eternity, quietly sculpting a future where time stretches into an unfathomable abyss. Whether the cosmos ends in ice, fire, or rebirth, one truth remains: we're witnesses to the universe's fleeting second act, alive in the narrow sliver of time when its mysteries are still within reach. And that makes every discovery, every observation, a message in a bottle tossed toward an unknowable shore. Among the most perplexing features of our universe are cosmic voids, vast, bubble-like regions where galaxies are almost entirely absent, some stretching hundreds of millions of light-years across. These aren't just empty patches, they're staggering deserts of near-nothingness, so devoid of matter that if you stood at the center of one, the night sky would appear almost pitch black, with only a handful of distant stars visible to the naked eye. But here's the twist: these voids might hold the key to understanding dark energy's true nature. Unlike the crowded galaxy clusters where gravity dominates, voids are where dark energy's subtle push might be magnified, warping space itself in ways that defy expectations. Take the Boötes void, a colossal emptiness roughly 330 million light-years wide. If our Milky Way sat at its center, astronomers wouldn't have discovered other galaxies until the 1960s. That's how sparse it is. Conventional models suggest voids should grow slowly, their edges eroded by gravity's tug from surrounding matter. Yet observations reveal they're expanding far faster than predicted, as if dark energy is working overtime in these regions. It's like blowing up a balloon and noticing certain sections stretch thinner, faster, without explanation. This anomaly has led to a radical idea. What if dark energy isn't uniform but fluctuates like temperature across the cosmos? In dense galaxy clusters, its effect could be muted, drowned out by gravity's pull. But in voids where matter's grip is weakest, dark energy might operate unchecked, accelerating expansion to extremes. Imagine walking through a forest where the wind is calm beneath the trees, but howls uncontrollably in open clearings. A cosmic version of this unevenness could explain why voids are growing so unnaturally fast. The implications are staggering. If dark energy behaves differently in voids, our entire cosmological framework might need retooling. The standard model assumes a smooth universe where dark energy's influence is evenly distributed. But voids suggest a patchwork cosmos with expansion rates varying wildly from region to region. This isn't just a tweak, it's a potential overthrow of one of cosmology's bedrock principles. Future telescopes like ESA's Euclid are poised to test this, mapping millions of voids to see if their growth betrays secrets about dark energy's rules, or lack thereof. Yet the real mystery runs deeper. Voids aren't just passive bystanders in cosmic expansion, they might actively shape it. Some theories propose these empty regions act like cosmic negative masses, their sheer lack of matter creating a repulsive effect that fuels dark energy's push. Others wonder if voids are fingerprints of an even stranger phenomenon, bubbles of alternate physics, where the fundamental constants of nature shift slightly. It's a haunting prospect. The emptiest places in the universe could be the very ones rewriting its laws. For now, voids remain one of cosmology's great unanswered riddles. They challenge not just our understanding of dark energy, but the very uniformity we assumed the universe obeyed. Every time we peer into these abysses of nothingness, we're confronted with the unsettling possibility that the cosmos is far weirder and far more nuanced than we ever dreamed. And that's the paradox. To solve the mystery of dark energy, we might need to study the places where almost nothing exists at all. For 13.8 billion years, the universe has been engaged in a cosmic tug-of-war, gravity pulling matter together, dark energy flinging it apart. But here's the twist. Dark energy didn't just slow the growth of galaxies, it rewrote the rules of cosmic architecture. Picture the early universe as a bustling metropolis, matter clumping into dense neighborhoods under gravity's relentless pull. Gas clouds collapsed, stars ignited, and galaxies merged in a frenzy of construction. Then, around 5 billion years ago, dark energy flipped the script. Suddenly, the cosmic city began sprawling outward faster than new structures could form, like subway lines extending into empty suburbs faster than builders could lay bricks. The evidence is etched into three-dimensional maps of the cosmic web, a sponge-like structure where galaxies cluster along filaments separated by vast voids. In the universe's youth, these filaments were thick with matter, glowing with the glow of newborn stars. But as dark energy's influence grew, the threads of the web began stretching thin. Galaxies at the edges found themselves stranded, their gravitational connections severed by the accelerating expansion. It's as if the universe switched from knitting a tight sweater to crocheting a net with ever-widening holes. The most dramatic casualties, galaxy clusters, the universe's megacities. Without dark energy, simulations show these clusters should be 10 times more massive today, with thousands of galaxies bound together in dense knots. Instead, we find them stunted, their growth stymied by the relentless stretching of space. The Virgo cluster, our local supercluster's heart, should be teeming with countless more galaxies. Instead, it's a modest hub, its suburbs fading into darkness as expansion whisks them away. Yet dark energy's impact isn't uniform. Peek into the distant past using telescopes like JWST, and you'll see galaxies forming at breakneck speed during the universe's first few billion years before dark energy took hold. Fast forward to today, and new galaxy formation has plummeted by 80%. The cosmic construction boom is over, its workers laid off by an invisible force. Even collisions between galaxies, once the universe's primary growth engine, are becoming rare events. The Milky Way's impending merger with Andromeda will be one of the last great galactic dances before the music stops. What's eerie is how perfectly this aligns with dark energy's timing. Had it dominated earlier, galaxies might never have formed at all later, and we'd see far more clustering today. Instead, we're left with a Goldilocks scenario, a universe that built just enough structure to create stars, planets, and us before dark energy turned off the lights. Future surveys like the LSST will map this transition in ultra-high definition, tracing how the cosmic web frayed under dark energy's grip. But for now, the lesson is clear. The universe's greatest structures didn't just stop growing, they were frozen in mid-construction, half-built monuments to a force we're only beginning to understand. String theory, that grand framework aiming to unify all forces of nature, might have just thrown a wrench into the dark energy puzzle. Enter the swampland conjectures, a set of rules that, if true, would exile most of our current dark energy theories to a metaphoric wasteland of impossible physics. These conjectures suggest that certain ideas, while mathematically elegant, can't possibly describe our actual universe because they destabilize the very fabric of reality. And dark energy, it turns out, might be caught in the crossfire. At the heart of the swampland is a brutal verdict: Einstein's cosmological constant, the simplest explanation for dark energy, might not survive contact with string theory. The math implies that a truly constant dark energy would require impossibly fine-tuned parameters, like balancing a pencil on its tip in a hurricane. Instead, the swampland favors dynamical models like quintessence dark energy that evolves over time, ebbing and flowing like a cosmic tide. Picture it as nature's way of saying, a universe with static dark energy. That's not just unlikely, it's forbidden. But why would string theory care? The issue lies in the theory's landscape, a dizzying array of possible universes, each with different physical constants. To build a stable universe, string theory demands certain conditions. Fields can't be too weak, energies can't be too flat, or the whole structure collapses into mathematical nonsense. The cosmological constant, with its perfectly uniform push, skirts dangerously close to these limits. Quintessence, by contrast, offers wiggle room. Its changing nature sidesteps the swampland's traps like a dancer weaving through obstacles. The implications are staggering. If the swampland conjectures hold, our entire understanding of cosmic acceleration might need a rewrite. Forget a universe coasting on a steady dark energy breeze. We'd live in one where that energy is slowly decaying, its strength tied to some deeper, unseen field. Future experiments could test this by hunting for minuscule changes in dark energy's strength over billions of years. Even a tiny drift would be a smoking gun, proof that we're not in a cosmological constant universe after all. Yet the swampland remains controversial. Critics argue it's too restrictive, a straitjacket on theoretical creativity. Others counter that it's a necessary filter, separating plausible physics from mathematical fantasy. Either way, it forces a thrilling reckoning. The universe's greatest mystery might not just be unsolved, it might be hinting at laws far stranger than we've dared to imagine. And that's the beauty of the hunt. Every dead end isn't a failure. It's a signpost pointing toward truths we're only beginning to glimpse. What if dark energy isn't just hiding in plain sight, but actively camouflaging itself? Enter chameleon theory, one of the boldest twists on the dark energy puzzle. Unlike the cosmological constant, which blankets the universe uniformly, chameleon particles would be master shapeshifters, altering their behavior based on surroundings. In the emptiness of space between galaxies, they'd exert a powerful repulsive force driving cosmic expansion. But in dense regions like Earth's neighborhood, they'd dampen their effects, slipping past detectors like cosmic ghosts. It's as if dark energy wears a disguise, blending into high-density environments to avoid detection while ruling the voids unchecked. This sleight of hand hinges on a hypothetical scalar field, a kind of invisible fluid permeating reality, whose strength varies with local matter density. Picture a chameleon changing colors. In sparse intergalactic space, the field's wavelength stretches long, pushing galaxies apart. Near massive objects like stars or planets, it compresses, shrinking its influence to near undetectable levels. The result, a dark energy that's not constant but adaptive, fine-tuning its presence to evade our instruments. The real magic lies in how this could explain dark energy's elusiveness. Despite dominating the universe's energy budget, no experiment on Earth or in the solar system has directly detected it. If chameleons exist, they'd be deliberately hiding here, suppressed by our planet's density. But scientists aren't letting them off the hook. In labs worldwide, researchers are designing exquisitely sensitive tests to flush out these cosmic fugitives. One approach uses ultra-precise atom interferometry, essentially dropping atoms in a vacuum and watching how they fall. Any deviation from gravity's expected pull could betray a chameleon field's subtle tug. Another experiment, the GAMV Chameleon project, fires laser pulses through a magnetic vacuum chamber, searching for telltale light oscillations that might occur if photons interact with hidden chameleon particles. It's like setting a trap with light and magnetism, waiting for dark energy to slip up. The stakes are sky high. If chameleons are real, they'd not only explain dark energy, but also offer a bridge between quantum physics and cosmology, a scalar field threading through all of reality. Yet failure to find them tightens the noose around other theories, like quintessence or modified gravity. Every null result is a clue, narrowing the possibilities toward an answer. What makes chameleon theory so electrifying is its audacity. It suggests dark energy isn't just an inert background actor but an active participant, dynamically interacting with the cosmos. And that changes everything. If true, we're not just mapping the universe's expansion, we're decoding its secret language, one hidden particle at a time. If dark energy plays by the rules, its strength should stay locked in place, a constant hum woven into the fabric of space-time. But the universe loves breaking expectations. Recent observations suggest this mysterious force might be more restless than we thought, its grip tightening or loosening over cosmic history. The clues lie in two seemingly unrelated phenomena: baryon acoustic oscillations, frozen ripples from the early universe, and the flickering light of quasars, the blazing hearts of distant galaxies. Together, they're painting a picture that's anything but static. Start with baryon acoustic oscillations, or BAO. These are cosmic fossils, echoes of pressure waves that rippled through the hot plasma of the newborn universe. When the cosmos cooled enough for atoms to form, these waves froze in place, leaving a telltale pattern. Galaxies today are slightly more likely to be separated by about 500 million light-years, a relic of those ancient vibrations. By measuring this cosmic ruler at different epochs, scientists can track how dark energy's push has altered the universe's expansion rate over billions of years. The result, BAOs suggest dark energy has held steady, its strength unwavering like a metronome ticking across the ages. Then comes the plot twist. Quasars, supermassive black holes guzzling gas so violently they outshine entire galaxies, tell a different story. When researchers used quasars as cosmic lighthouses, mapping how their light stretches as space expands, they found a puzzling deviation. The data hinted that dark energy might have been stronger in the universe's adolescence around 10 billion years ago before easing into its current state. It's as if the cosmos had a rebellious phase, with dark energy flexing its muscles before settling down. The discrepancy isn't just academic, it's a potential seismic shift in our understanding. If BAOs and quasars can't agree, either our measurements are flawed, or dark energy is far more dynamic than Einstein's cosmological constant allows. Some theorists speculate that dark energy could interact with dark matter, its strength waxing and waning as these two shadowy components engage in a cosmic tug of war. Others wonder if we're seeing the fingerprints of extra dimensions where gravity leaks between realities, subtly altering dark energy's effects over time. The stakes couldn't be higher. If dark energy varies, it could rewrite the universe's fate. A strengthening force might spell doom via the Big Rip, while a weakening one could allow gravity to reclaim dominance, triggering a cosmic collapse. Right now, projects like the Dark Energy Spectroscopic Instrument are racing to settle the debate, mapping millions of galaxies and quasars to see which narrative holds. Every new data point pulls us closer to an answer or deeper into the mystery. What makes this hunt so electrifying isn't just the science, it's the sheer audacity of the questions. We're not just asking what dark energy is, we're asking whether it's a constant in the equations or a shapeshifter, quietly rewriting the rules when we're not looking. And that uncertainty, that's where discovery begins. Dark energy's peculiar strength, just enough to accelerate cosmic expansion without instantly tearing reality apart, has led some scientists down a rabbit hole of cosmic conspiracy. Why does this mysterious force have such an unnervingly perfect value? One radical answer whispers from the edges of physics: perhaps our universe isn't alone. Imagine a cosmic lottery where countless universes flicker into existence, each with randomly assigned physical constants. Most would collapse immediately or expand too fast for galaxies to form. But a rare few, like ours, strike the delicate balance needed for life. This isn't just wild speculation, it's the controversial heart of the multiverse anthropic argument. String theory's landscape paints a dizzying picture: 10 to the 500th power possible universes, each with different laws. In that unimaginable ensemble, dark energy's value in our universe stops looking like a fluke and starts resembling selection bias. We exist here because this is one of the few places where the numbers allowed observers to emerge. Think of it like tuning a radio. Most stations are static, but twist the dial just right and you hit music. The station we're listening to happens to have dark energy's volume set at life-permitting levels. Critics recoil at this reasoning, calling it science-stopping philosophy. They argue the anthropic principle excuses us from seeking deeper explanations. Why bother hunting for fundamental laws if we can chalk everything up to statistical luck across infinite worlds? But supporters counter that some features of reality, like dark energy's absurdly tiny but non-zero value, defy traditional explanation. Quantum field theory predicts vacuum energy should be 120 orders of magnitude stronger than observed. That's not just wrong. It's catastrophically wrong, like predicting a candle's flame would vaporize a city. The multiverse offers a way out. Most universes do have deadly vacuum energies. We just don't live in those. Observational clues might lurk in the cosmic microwave background. Some models suggest colliding universes could leave bruises in this primordial light-cold spots or unusual polarization patterns. Others propose that if dark energy varies across the multiverse, its effects could imprint on large-scale galaxy distributions, creating subtle asymmetries in the cosmic web. Projects like the Simons Observatory are scanning for these anomalies, hunting for fingerprints of other universes in the static of our own. Yet the debate rages fiercer than a supernova. Nobel laureates line up on both sides, some calling the multiverse testable science, others dismissing it as metaphysics dressed in equations. What makes this more than academic sparring is the looming question. If dark energy's value isn't fundamental but circumstantial, does that mean the laws of physics aren't laws at all? Just local bylaws in a cosmic megalopolis we'll never see. The answers, if they come, won't just redefine dark energy, they'll rewrite what science itself can aspire to know. Black holes have long been the universe's ultimate enigmas, cosmic traps where gravity becomes so strong not even light escapes. But what if these dark monsters hold a secret connection to dark energy? A radical idea is gaining traction, that black holes might be growing faster than physics allows because their cores contain vacuum energy intricately linked to the force accelerating the universe's expansion. This isn't just theoretical hand-waving. Observations of supermassive black holes at the hearts of galaxies show they're packing more mass than traditional models can explain, as if they've been feeding on something invisible. The key lies in a hypothesis called cosmological coupling. Picture a black hole not as a static pit in spacetime, but as a dynamic entity whose mass increases as the universe expands. According to this theory, the vacuum energy inside black holes, the same repulsive force driving cosmic acceleration, might be fueling their growth. It's like blowing up a balloon and noticing the ink dots on its surface don't just spread apart, they swell in size, absorbing energy from the stretching rubber itself. If true, this would mean black holes aren't just passive prisoners of gravity. They are active participants in the cosmos's expansion, their very existence tied to dark energy's mysterious push. The implications would rewrite astrophysics. First, it could solve the missing mass problem in early galaxies, where black holes appear inexplicably massive for their age. If cosmological coupling is real, these black holes didn't just grow by swallowing stars, they expanded along with the universe, their mass increasing in lockstep with dark energy's influence. Second, it hints at a profound symmetry. The same force stretching galaxies apart might also be pumping energy into the darkest objects in existence. But skeptics aren't sold. Traditionalists argue black holes gain mass solely through accretion, pulling in gas and stars, or mergers with other black holes. The idea that they could grow for free, fueled by cosmic expansion, seems to violate energy conservation. Others point to alternative explanations like measurement errors or overlooked astrophysical processes. Yet the data keeps teasing. Recent studies of ancient black holes, some dating back to just 700 million years after the Big Bang, show masses that cosmological coupling could neatly explain where conventional models strain. The paradox cuts deeper. If black holes truly are repositories of vacuum energy, their eventual evaporation via Hawking radiation could release dark energy back into the cosmos, a feedback loop spanning billions of years. Imagine a universe where dying black holes don't just fade away, they return their stored repulsive energy to the void, like batteries discharging into the fabric of spacetime. Future gravitational wave observatories like LISA might detect subtle ripples betraying this process, offering a glimpse into black holes' hidden connection to dark energy. For now, the idea remains tantalizingly unproven, a thread in the tapestry of cosmic mysteries, but that's the thrill of the hunt. Every time we think we've pinned down the rules, the universe whispers a new riddle. And this one, it suggests the darkest places in existence might hold the brightest keys to understanding everything. Imagine waking up one day to discover your entire neighborhood was built inside a colossal sinkhole, while the rest of the world sprawled normally beyond its edges. This unsettling idea isn't just a thought experiment, it's a serious challenge cosmologists call the void hypothesis, suggesting dark energy might not be real at all. Instead, what if we're simply floating in a vast, underdense bubble of space, where the lack of surrounding matter creates the illusion of cosmic acceleration? It's a radical twist on Copernicus' old lesson. Maybe we aren't in an average part of the universe, but an accidental outlier. The math is deceptively simple. In general relativity, empty regions expand faster than matter-rich ones, like a stretched rubber sheet sagging where weights are absent. If our Milky Way resided in a void spanning billions of light years, the outward rush of galaxies we measure could just be gravity's weaker grip here, not some mysterious dark energy. Picture standing in a valley surrounded by mountains. The landscape might look like it's rising away from you, but in reality, you're just standing in a dip. Proponents point to eerie consistencies like how such a void could mimic dark energy's apparent strength, while neatly sidestepping its theoretical headaches, like the cosmological constant problem. But there's a catch. For this illusion to hold, the void would need to be impossibly large, at least 700 million light-years wide, placing us suspiciously close to its center. That violates the Copernican principle, which holds that Earth holds no privileged cosmic position. It's like claiming every map ever made is wrong because your backyard happens to be the true center of the world. Worse, voids this size should distort the cosmic microwave background in ways Planck's satellite data simply doesn't show. The universe's oldest light appears too uniform, too balanced to support such a lopsided structure. Yet the debate isn't dead. Some scientists suggest a compromise, a not-quite-void scenario where our local universe is slightly emptier than average, enough to tweak measurements but not append cosmology. Others propose exotic voids with intricate density gradients that might dodge observational constraints. Future galaxy surveys like Euclid could settle this by mapping matter distribution in unprecedented 3D, revealing whether we're truly in a cosmic backwater or part of a grander, darker narrative. What makes the void hypothesis so tantalizing isn't just its audacity, it's the reminder that even our best theories rest on assumptions. If something as foundational as the universe's uniformity can be questioned, what other pillars might tremble under scrutiny? For now, dark energy remains the leading explanation, but the void whispers an unsettling alternative. Perhaps the greatest mystery in cosmology isn't a force at all, but a trick of perspective, one we're only beginning to see through. At the heart of dark energy lies a quantum conundrum so baffling it's been called the worst theoretical prediction in the history of physics. According to quantum mechanics, empty space isn't truly empty. It's a seething quantum foam where particle-antiparticle pairs constantly wink in and out of existence. These fleeting quantum fluctuations should imbue every cubic centimeter of vacuum with a staggering amount of energy, creating what physicists call the zero-point energy of the universe. Here's where things get wild. When you calculate how much energy this quantum frenzy should contribute to dark energy, the numbers blow past reality by a factor of 10 to the 120th power. That's a 1 followed by 120 zeros, a discrepancy so enormous it's like predicting a single grain of sand could outweigh the entire Milky Way. This mind-bending mismatch is known as the cosmological constant problem, and it exposes a glaring rift between quantum theory and cosmology. On one hand, quantum field theory treats empty space as a stormy sea of virtual particles, each contributing a tiny burst of energy. Sum them all up, including particles we haven't even discovered, and you get a vacuum energy density that should make the universe rip itself apart in a fraction of a second. Yet observations show dark energy's actual strength is ludicrously weaker, as if all those turbulent quantum waves somehow cancel out to near-perfect silence. It's like expecting the roar of a hurricane but hearing only the faintest whisper. Physicists call this cancellation fine-tuning, and it reeks of impossibility. For the observed dark energy value to emerge naturally, the positive and negative contributions from quantum fields would need to balance to 1 part in 100 trillion 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 trillion. That's not just unlikely, it's like shuffling a deck of cards and getting them to arrange perfectly by suit and number every single time. Some theorists argue this points to undiscovered symmetries or hidden mechanisms that automatically zero out vacuum energy. Others suspect our understanding of quantum gravity. The missing link between quantum mechanics and general relativity holds the key. the plot thickens with renormalization, a mathematical trick physicists use to tame infinity in quantum calculations. By artificially subtracting divergent terms, they can extract sensible predictions about particle behavior. But when applied to vacuum energy, renormalization fails spectacularly, leaving behind those absurdly huge values. It's as if the universe applied its own undiscovered renormalization scheme, trimming the fat until only dark energy's faint imprint remained. String theorists propose their framework might solve this. Perhaps higher dimensions or vibrating brains soak up excess energy like cosmic sponges. Yet for all the theoretical gymnastics, one haunting question lingers. What if the mismatch isn't a flaw but a clue? Could dark energy's eerie smallness hint at deeper layers of reality, extra dimensions, parallel universes, or laws that rewrite physics at cosmic scales? The stakes couldn't be higher. Cracking this puzzle wouldn't just explain dark energy, it might reveal the hidden rules stitching quantum weirdness and cosmic expansion into a single, coherent tapestry. Until then, the quantum vacuum remains the universe's most extravagant party, hosted in a space so vast and mysterious we've barely begun to RSVP. What if dark energy isn't woven into the fabric of space itself, but projected onto it like a cosmic hologram? This mind-bending possibility comes from the holographic principle, a radical framework suggesting our three-dimensional universe might be nothing more than information encoded on a two-dimensional surface at its edge. It sounds like science fiction, but the math behind this idea is rooted in black hole physics and string theory's most daring conjectures. And if it's true, dark energy could be less about mysterious vacuum energy and more about how reality itself computes its own existence. The story begins with an unexpected link between black holes and thermodynamics. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes possess entropy, a measure of disorder that somehow corresponds to the area of their event horizons, not their volume. This was bizarre. In everyday physics, entropy scales with volume. Think of a gas filling a room. But black holes suggested information about their contents might be painted on their surfaces, like a cosmic hard drive storing data in pixels at the boundary. Fast forward to the late 1990s, when string theorists like Juan Maldacena proposed the AD/S/CFT correspondence, a concrete realization of this holographic idea. It showed a universe with gravity like ours could be mathematically equivalent to a quantum field theory operating on its boundary, no gravity required. Now here's where dark energy enters the picture. If our universe is holographic, its expansion might not be driven by energy within space, but by information processing on its edge. Think of it like a computer simulation struggling to render an ever-expanding world. The more space grows, the more pixels are needed, and the system compensates by stretching spacetime itself. Dark energy, in this view, could be the computational cost of maintaining consistency across the projection, a glitch in the cosmic code that's causing the universe to scale faster than intended. Supporters point to eerie coincidences. The observed value of dark energy fits suspiciously well with holographic models where the universe's information budget is tied to its surface area. It's as if the cosmos is obeying a hidden data limit, with dark energy emerging as a byproduct. Critics counter that the holographic principle remains untested, a beautiful mathematical metaphor without observational proof. But upcoming experiments might change that. If spacetime truly has a pixelated structure at the tiniest scales, gravitational wave detectors like LISA could spot the fuzziness, like noticing the graininess of a projected image when zooming in close. The implications are staggering. If holography explains dark energy, we're not just uncovering a new force, we're decoding the operating system of reality itself. Maybe dark energy isn't a thing at all, but a shadow cast by deeper rules governing how information shapes existence. And that's the real magic of this idea. It turns the greatest mystery in cosmology into a cosmic error message, beckoning us to look beyond the screen. What if dark energy isn't leaking away but leaking in? String theory's most tantalizing prediction isn't just extra dimensions folded into microscopic loops. It's the possibility that dark energy might be seeping into those hidden layers, like water soaking into unseen cracks in a cosmic foundation. Imagine gravity as a force that doesn't just tug along the three dimensions we know, but spills into higher spatial realms we can't perceive. If true, that could explain why dark energy feels so faint in our universe. It's not vanishing, but diffusing across dimensions we're blind to. The math gets wild here. In some string theory models, our four-dimensional spacetime floats like a membrane or brain within a higher dimensional bulk. Gravity, unlike other forces, isn't confined to our brain. It can spread into the bulk, diluting its strength in our observable universe. Dark energy might behave similarly, its repulsive push weakened because part of its influence is leaking away into these unseen dimensions. It's like trying to fill a bathtub with a hole in the bottom. The water level stays low not because the tap is weak, but because the water's escaping somewhere you can't see. Colliders like the Large Hadron Collider might hold clues. While we can't directly probe extra dimensions, we could spot their fingerprints in missing energy during particle collisions. If high-speed protons smash together and some energy mysteriously vanishes, it might have tunneled into hidden spatial folds, carrying dark energy's secrets with it. The catch: these effects would be infinitesimally small, like detecting a whisper in a hurricane. Yet upgrades to the LHC and future colliders, like the proposed Future Circular Collider, aim to sharpen their sensitivity to such ephemeral signals. The implications are dizzying. If extra dimensions siphon off dark energy, it would mean our universe's accelerating expansion isn't just a local phenomenon, it's entangled with geometries we can't yet map. It also hints at a deeper symmetry. The same higher dimensional fabric that gives rise to gravity's weakness might govern dark energy's elusive strength. For now, these ideas dance on the edge of testability, but that's where the most electrifying science happens, where the universe's boldest mysteries force us to rewrite the rules. Neutrinos are the universe's most elusive particles, tiny, nearly massless ghosts that stream through matter as if it weren't even there. Billions pass through your body every second, leaving no trace. Yet these cosmic specters might hold a clue to dark energy's deepest secrets. For years, physicists assumed neutrinos were massless, moving at light speed without hesitation. Then came the bombshell. They oscillate, shifting between three different flavors as they travel, a quantum magic trick that only works if they have mass. But here's where things get even stranger. Those vanishingly small masses don't quite add up the way they should. Some experiments detect more oscillations than predicted, as if neutrinos are flickering in and out of existence faster than the math allows. Could the missing piece be dark energy? Take the anomaly seen in neutrino detectors like Mini, BUNI, and LSND. These experiments recorded more electron-neutrino appearances than standard models predict, a mismatch some theorists attribute to a hypothetical sterile neutrino, a fourth flavor that doesn't interact via any known force except gravity. But another possibility is even more intriguing. What if sterile neutrinos don't exist, and the excess oscillations are instead a sign of neutrinos brushing up against dark energy's hidden field? Picture it like a swimmer battling an unseen current. Their path veers unexpectedly, not because of anything in the water, but because the river itself is pushing back. The math gets wilder when you consider how neutrinos might couple to dark energy. In some theories, neutrinos act as cosmic messengers, their oscillations sensitive to the density of dark energy in their environment. As the universe expands and dark energy's influence grows, neutrinos could oscillate differently depending on when and where they're born. It's as if these particles carry a built-in dark energy sensor, changing their behavior based on the era they traverse. If true, studying neutrinos from supernova or the sun's core might reveal subtle shifts correlated with cosmic acceleration, a smoking gun hidden in the flickering of the universe's faintest particles. Even more tantalizing is the idea that neutrinos and dark energy might share a common origin. In certain grand unified theories, both emerge from the same primordial symmetry breaking, like two sides of a coin split apart at the dawn of time. If neutrinos acquired their tiny masses through a mechanism linked to dark energy's repulsive force, it would mean these particles aren't just passive bystanders in cosmic expansion but active players. They're quantum dances woven into the fabric of spacetime itself. The challenge: neutrinos are infamously hard to pin down. Catching enough of them to spot these subtle effects requires detectors the size of office buildings buried deep underground, like Japan's Super Kamiok or the upcoming Deep Underground Neutrino Experiment. But if anomalies in their behavior do trace back to dark energy, the payoff would rewrite physics. Suddenly, the universe's most abundant yet elusive particle becomes a key to understanding its most mysterious force, a bridge between the quantum world and the cosmos's accelerating fate. For now, the connection remains speculative, a shadow on the edge of our theories. But in the hunt for dark energy, even ghosts might leave footprints. Back in the 1970s, as NASA's twin Pioneer probes hurtled toward the outer solar system, engineers noticed something bizarre: they were slowing down. Not from friction or gravity, but by an amount so slight it shouldn't have mattered, about 9 billionths of a meter per second squared. Yet over decades, that tiny deceleration added up, pulling the spacecraft off course by hundreds of kilometers. Scientists dubbed it the Pioneer anomaly, and for years it lingered as one of spaceflight's quietest mysteries. Conventional explanations trickled in. Perhaps heat radiating unevenly from the probe's nuclear batteries nudged them backward, or maybe sunlight's faint pressure played a role. But when researchers painstakingly modeled these effects, the math never quite lined up. The anomaly stubbornly refused to vanish, whispering of forces unaccounted for. Then came the radical twist. What if Pioneer's slowdown wasn't a fluke of engineering, but a faint echo of dark energy's grip? At first glance, it sounds absurd. Dark energy drives galaxies apart at accelerating speeds, not slows spacecraft. But fringe theories propose that dark energy might interact differently in regions of extreme gravitational dominance like our solar system. Picture a cosmic tug-of-war. On galactic scales, dark energy overpowers gravity's pull, but near massive objects like the Sun, gravity could locally warp its effects, creating subtle drag. If true, Pioneer's trajectory might have been the first human-built experiment to brush against dark energy's shadow. Skeptics pounced. The solar system is far denser than the intergalactic voids where dark energy dominates. Its influence here should be negligible. Others argued that even if dark energy did leak inward, its repulsive nature would push Pioneer faster, not slower. Yet alternative models suggest dark energy's behavior might flip in strong gravitational fields, acting more like a viscous medium, a cosmic molasses resisting motion. Wild as it sounds, similar ideas emerge from modified gravity theories, where small-scale deviations from Einstein's equations could mimic an extra drag force. The debate took another turn in 2012 when a team analyzing decades of telemetry announced the culprit was likely mundane. Heat from Pioneer's electronics, radiating anisotropically, provided just enough thrust to explain the anomaly. Case closed, or so it seemed, but dissenting voices remain. Some argue the heat model still leaves a residual drift unaccounted for, while others point to Cassini, a later probe that showed no such deceleration despite similar design. If heat alone can't explain the discrepancy, could there still be room for exotic physics? What makes the Pioneer anomaly so captivating isn't just the unresolved questions. It's the reminder that even our own cosmic backyard might hide clues to the universe's deepest secrets. Whether a thermal quirk or a whisper of dark energy's hidden face, those drifting probes taught us something profound. Sometimes the smallest anomalies point to the biggest revolutions. And in the hunt for answers, even dismissed data can resurface as cosmic breadcrumbs. Could dark energy be tied to consciousness itself, an invisible force responding to the act of observation like some cosmic puppet master? At first glance, it sounds like science fiction, but this bizarre connection emerges from a collision of quantum weirdness and cosmological mystery. The spark ignites with a measurement problem in quantum mechanics, the unsettling fact that particles seem to exist in multiple states until observed when they suddenly choose a definitive position. Some radical theorists take this further, proposing that consciousness isn't just recording reality but actively shaping it, with dark energy as the hidden mediator. Before dismissing this as New Age mysticism, let's dissect where physics ends and speculation begins. Start with quantum physics' legitimately strange observer effect. In experiments like the double-slit test, particles behave as waves when unobserved, creating interference patterns. But the moment scientists measure which slit they pass through, they snap into particle-like behavior. Mainstream interpretations like the Copenhagen interpretation attribute this to interactions with measuring devices, not human minds. Yet the line blurs in proposals like von Neumann-Wigner consciousness theory, where observation by a conscious entity collapses quantum states. Push this idea to cosmic scales and you get wild conjectures. Could the universe's accelerating expansion be driven by some form of universal observation? One fringe hypothesis suggests dark energy is a feedback loop, conscious observers like humans stabilizing reality through measurement, with each act of observation releasing tiny bursts of repulsive energy. It's an intoxicating idea, evoking cosmic purpose, but the scientific hurdles are staggering. For starters, there's no known mechanism linking quantum-scale observation to galaxy-pushing dark energy. The energy scales differ by dozens of orders of magnitude, like claiming a candle's flicker could power a supernova. Worse, it smacks of anthropocentrism. Why would consciousness suddenly matter 5 billion years ago when dark energy turned on? Still, the conversation isn't entirely meritless. Roger Penrose's orchestrated objective reduction or theory proposes quantum processes in brain microtubules might interface with spacetime geometry. While controversial, it at least grounds consciousness in testable biophysics rather than cosmic mysticism. Even here, though, the leap to dark energy remains speculative. More plausible is the idea that consciousness and dark energy simply share a common quantum vocabulary entanglement, non-locality without direct causation. The real danger lies in conflation. Quantum mechanics observer effect deals with information exchange, not sentience. Meanwhile, dark energy's effects are purely gravitational, detectable through galactic recession, not brain waves. Yet the persistence of these theories reveals something profound, our discomfort with a universe indifferent to observation. We crave meaning, a cosmos that responds to our gaze. Dark energy, as the ultimate unseen force, becomes a blank screen for projection, whether as cosmic consciousness or physics' cold equations. The truth, as always, is likely stranger than fiction, waiting where rigorous science dares to explore. The next decade could rewrite everything we know about dark energy, thanks to a fleet of cutting-edge telescopes poised to scan the cosmos with unprecedented precision. Leading the charge is the European Space Agency's Euclid spacecraft, a dark energy hunter armed with a billion-pixel camera and a near-infrared spectrometer. Unlike Hubble, which captures stunning portraits of individual galaxies, Euclid will map billions of them across 10 billion light-years, tracing how their clustering and shapes warp under dark energy's invisible hand. Imagine unraveling the universe's expansion history not from a handful of landmarks, but from a cosmic census so vast it reveals patterns no single galaxy could betray. Then comes NASA's Nancy Grace Roman Space Telescope, slated to launch by 2027. Roman isn't just another observatory, it's a time machine. By peering back to the universe's teenage years, around 2 billion years after the Big Bang, it could catch dark energy in its transitional phase. Did it kick in abruptly, or was its rise a slow crescendo? The telescope's wide-field instrument will survey thousands of supernovae, comparing their brightness to those in our cosmic neighborhood. If dark energy's strength has wavered over time, Roman's data could expose it like a detective spotting inconsistencies in a suspect's alibi. But the real game-changer might be the Square-Kilometre Array, or SCAR radio telescope so vast its antennas will span continents from South Africa to Australia. Instead of light, SKA listens to the faint whispers of hydrogen atoms, the universe's most abundant element. By tracking how hydrogen clouds distort as space stretches, SKA could measure dark energy's push with a precision 10 times sharper than current methods. It's like swapping a sundial for an atomic clock. Suddenly, tiny fluctuations in cosmic expansion become glaringly obvious. What makes these missions revolutionary isn't just their technology, it's their synergy. Euclid maps galaxies in optical and infrared, Roman hunts supernova, and SK charts hydrogen's cosmic ballet. Cross-referencing their data could reveal whether dark energy is truly uniform or patchy, constant or evolving. If their findings align, we might finally pin down dark energy's true nature. If they clash, that's when things get thrilling. Discordant results could signal entirely new physics. Perhaps dark energy interacts with dark matter, or maybe Einstein's gravity equations fracture at cosmic scales. The stakes are almost unimaginable. With enough precision, these probes might uncover whether the universe's fate is a cold fade out, a catastrophic rip, or something even stranger. For the first time in history, we're not just speculating about dark energy, we're building the tools to interrogate it, and the answers, whatever they are, will echo far beyond astrophysics textbooks. They'll redefine our place in a cosmos whose deepest rules are still being written. The laws of physics as we know them rest on 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But what if dark energy is hinting at a 5th player in this cosmic game? Some theorists propose that the mysterious push accelerating the universe might not just be a passive energy filling space, it could be the signature of an entirely new force, one that operates beyond the reach of our current equations. Unlike gravity's relentless pull, this 5th force might only reveal itself on colossal scales, tugging galaxies apart while leaving stars and planets untouched. Testing such an idea requires more than just peering at distant supernova. It means probing the fabric of reality at its smallest scales. If a 5th force exists, it could subtly alter how gravity behaves over tiny distances, deviating from Newton's trusted inverse square law. Picture this: at the macro scale, gravity weakens predictably with distance. Stand twice as far from Earth, and its pull drops to a quarter. But if dark energy's hidden force interacts with gravity at microscopic levels, that tidy relationship might fray. Experiments using exquisitely sensitive torsion balances, devices that measure gravitational attraction between minuscule masses, have scoured distances down to the width of a human hair, searching for any hint of an extra tug or push that shouldn't be there. One of the most ambitious efforts, the Earth Wash experiment at the University of Washington, spins gold-coated disks near equally precise detectors, hunting for deviations in gravitational force at scales smaller than a millimeter. So far, Newton's law holds firm, but the search isn't over. Other teams are designing experiments using ultra-cold atoms or microscopic cantilevers, hoping to catch the 5th force in the act. The challenge: distinguishing it from background noise like vibrations or electromagnetic interference is like listening for a whisper in a thunderstorm. Yet the implications of finding such a force would be revolutionary. It could mean dark energy isn't just an inert backdrop to the cosmos, but an active participant, mediating interactions we've yet to perceive. Some models even suggest this force could grow stronger over time, explaining why dark energy's influence seems to be winning against gravity. Others speculate it might operate through hidden dimensions, leaking into our universe only under specific conditions. The hunt is far from conclusive, but that's what makes it thrilling. Whether the fifth force remains a tantalizing hypothesis or becomes the next pillar of physics, the quest itself is reshaping how we probe the universe's deepest secrets, not just with telescopes, but with tabletop experiments that bring the cosmos into the lab. And that's the beauty of this mystery. The answer might not lie in the distant heavens, but in the quiet spaces between the atoms right in front of us. Dark energy doesn't just defy explanation, it defies reason. Here we are, creatures of stardust and curiosity, staring into the cosmic abyss, asking the most humbling question of all. Why? Why does the universe contain this relentless, invisible force, this anti-gravity that thwarts all expectations? It's not just a scientific puzzle, it's a cosmic riddle that forces us to confront the very nature of existence. Think about it. Dark energy isn't some minor detail in the grand scheme of things. It's the dominant ingredient in the universe, the unseen architect shaping everything from the fate of galaxies to the destiny of time itself. And yet we have no idea why it's here. Consider the alternatives. If dark energy were slightly stronger, the universe would have expanded too rapidly for stars, planets, or life to ever form. If it were weaker, gravity might have collapsed everything back into a cosmic crunch long ago. Instead, it's just the right strength to allow galaxies to assemble, and then tear them apart at the exact moment intelligent life arises to witness it. This isn't just a coincidence, it's a cosmic tightrope walk so precise it borders on the absurd. Some call it the Goldilocks enigma, a universe fine-tuned to an almost suspicious degree. But here's where it gets even stranger. Dark energy's existence challenges not just how the universe works, but why it works this way at all. Physics is built on cause and effect, on particles and forces interacting through measurable laws. Yet dark energy feels like an anomaly, a glitch in the matrix. It doesn't emerge naturally from any known theory. It doesn't play by the rules we've spent centuries uncovering. It's as if the universe handed us a beautifully wrapped gift, only to reveal the box is empty. Perhaps the most unsettling possibility is that dark energy isn't an accident but a feature. Some theories suggest it's the inevitable byproduct of a deeper structure, like quantum foam bubbling up into the cosmos. Others propose it's a shadow of something far grander, extra dimensions vibrating beyond our perception, or even the residue of a universe that came before ours. Then there's the multiverse argument. In an infinite sea of universes, each with random physical constants, we simply live in the one where dark energy's value allowed life to exist. But that raises another question. If dark energy is a cosmic lottery ticket, why does it feel like we've hit the jackpot? The search for answers isn't just about equations and telescopes, it's about meaning. Dark energy forces us to reckon with the idea that the universe might not owe us an explanation. It's a reminder that reality, for all its splendor, operates on terms we're still struggling to decode. Every observation, every experiment, every sleepless night spent staring at data brings us closer to the edge of understanding, only to reveal how much further there is to go. And that's the beautiful paradox. The more we learn about dark energy, the more we realize how little we know. It's not just the mystery of what it is or how it works, it's the awe of standing before something so vast, so fundamental, that it redefines the questions themselves. In the end, dark energy isn't just a puzzle to solve. It's a mirror held up to the limits of human curiosity, asking us, how far are you willing to go? The universe whispers its secrets in a language we're only beginning to understand, and the most thrilling part, we're just starting to listen. we've journeyed through 25 of the universe's greatest enigmas, from dark energy's phantom push to cosmic voids that defy logic, from black holes harboring vacuum energy to the unsettling possibility that we're floating in a colossal void. Yet here's the stunning truth: every answer we've uncovered only reveals deeper layers of mystery. For all our telescopes and equations, we've barely scratched the surface of reality. The cosmos seems determined to remind us just when we think we're close to understanding. It throws open a door to 10 new questions we never thought to ask. This isn't failure, it's the exhilarating essence of exploration. Centuries ago, we believed the stars were fixed lights on a celestial dome. Today, we measure their light for clues to dark energy's grip on spacetime. Who knows what revelations tomorrow holds? Perhaps the key lies in quantum foams seething chaos or holographic codes at the edge of reality. Maybe the solution will come from an experiment not yet imagined, a theory not yet scribbled on a chalkboard. That's the thrill of cosmic detective work. The next breakthrough could be lurking in data we've already collected, waiting for a fresh perspective to bring it into focus. So let's keep questioning. Let's stay dazzled by the unknown. Whether you're fascinated by the Hubble tension's stubborn contradictions, chilled by the Big Rip's apocalyptic potential, or captivated by the possibility of extra dimensions, every curious mind adds to this grand investigation. The universe isn't just expanding, it's inviting us to grow with it, to stretch our imaginations beyond comfortable limits. Now it's your turn. Which of these cosmic riddles keeps you up at night? The eerie fine-tuning of dark energy's strength, the way it might be hiding in plain sight as a chameleon field. Or something wilder still? Drop your thoughts below, because the next big idea might start with a conversation like this one. After all, in a universe where 95% of everything remains undiscovered, curiosity isn't just a trait, it's our compass.